My name is Bryan Shuman. I am so glad to be here with all of you this evening. Thank you so much for coming. I am a professor of geology and geophysics at the University of Wyoming down in Laramie. And I am so glad to be here as part of this collaborative effort to really engage all of you and others in this community to think about the future of climate change here. And I really appreciate the Teton County Library for hosting this, and for the Jackson Hole Center for Global Affairs for co-sponsoring, as well as the Geologists of Jackson Hole. Nathan Wendt and Lindsay Ehringer and Kay Modi were so essential in helping get this set up. And also thanks to Cynthia Blankenship for helping on the technology end from the Geologists of Jackson Hole. The whole point of this evening is to be kind of a choose your own adventure discussion a bit about climate change here. And I'm going to be speaking from the perspective of work that we've been doing at the university in collaboration with a number of people here in the region. And it's been supported by the National Science Foundation. So I also want to kind of make sure to thank them for all their support. So I want to get us started here by actually asking you to, we're going to try to do this in an engaged virtual technology way. And so throughout the talk or throughout the evening, there's going to be a number of opportunities for you to chime in and contribute. And so if you can use your phone to connect to this QR code, the QR code will lead you to a website that will let you answer the questions that I bring up throughout the presentation this evening. So if you just point your camera at that little link should come up. You don't even have to take a picture of it. You just click on that link. And it should lead you to right now, it should lead you to questions, and you have the opportunity to put in some words like, what are the things that concern you about how climate change might affect this region? And hopefully we'll start to get some of your answers up here on the screen. I'm really curious to learn what you're all most concerned about and what would like to think about. And this evening, we'll try to spend time touching on a wide range of topics that are of interest to you. If you need to, you can use the Teton County Library public web Wi-Fi as well, if that helps you connect. But I can see a number of people are getting in there and putting in your thoughts. So yeah, I see water and snow and drought figuring in prominently in some of the answers, but lots of other topics as well that hopefully we can spend some time on this evening to really to dig into. Give it a couple more moments here for people to use this. And by the way, a couple of things I'll just highlight. If you're having trouble with the technology and you have a question or something that you want to pass on to me, you can write them on these note cards. And Ashley and Caitlin, who are sitting over here by the window, will at various points come around to collect these if you need to write down your questions. The other thing I want to point out is that we've just released these 3 fact sheets about climate change in this region. And just try to give some more information beyond listening to me tonight. If you want to take these home and read them, we're working over the next few years on trying to write a report, a Snake River Headwaters climate assessment, basically a Teton County assessment of how climate is changing here. And these are sort of the seeds, sort of little hints as to what might be in there. So there's one talking about how temperatures have been changing historically, one about the projections of temperature change in the future, and one about snow and how it might change in the future. And we'll touch on those topics tonight as well. All right, well, thank you so much for filling this out. I'm so interested to see what you're interested in. And so I see, yeah, things like wildlife and fire and drought and snow and water really jumping out in a lot of people's answers. And we'll come back and look at some of these other topics too. I see things like insurance tucked in there. And I know I actually have planned to talk a little bit about that. Okay, so I am here in part representing this project that we call WYACT. It's Wyoming Anticipating the Climate Transition. And it involves about 20 different faculty at the University of Wyoming, spanning from atmospheric sciences all the way to economics, and a lot of different research scientists and postdocs and graduate students who are all involved. And we've had fantastic collaborations with a number of people up here from different agencies and organizations. And so we're about midway through this project. And our goal really is to try to help communities like Jackson think about how we might be affected in the near future. And so that's why I was so interested to see what your thoughts were getting started here. Tonight, I'll kick things off by showing you some information about how climate has been changing here, but also some updated projections about how it might change in the future. And this is work coming from a number of our atmospheric science colleagues. Pramod Adhikari is kind of the key lead person here, but Stefan Rahimi and Bart Gertz are the two faculty members leading this. And this map there shows you the region that they've really focused on, trying to simulate not just at the very large scale, but coming all the way down to simulating like different 3-kilometer grid points and how they're different from each other. So we can really get the details of the region and how it might change. So this is an important part of some of the work I'll show you. We also are interested in thinking about the impacts of climate change. So not just how the climate physically is going to change, but also how might it affect things like the flow regimes of the Snake River. How will that impact trout populations? What are some of the recreational or I want to start off though, just thinking about all those topics that you just put into the survey there. And to me, those all touch on this bigger issue of like, how will this place change? And I've often, when I've spoken about it before, used this photo from Ansel Adams in 1942. You know, this is kind of the iconic view of the Snake River and the Tetons. And you can see the snow and all the important water in the river, of course, and think about this whole landscape. And in many ways today, it doesn't look that different than it did in 1942. But the challenge for us is imagining what's it going to look like in 2042? What's going to be different about that? And, going further, of course, out into the future. But in many ways, I think we often talk about climate change as something that's going to happen at the end of the century, but it's already beginning. And it is, I think there may be significant changes by the time we get to 2042. And so one of our goals has been to really think collectively about what to anticipate, what changes should we prepare for. There's so much important work going on to try to mitigate our carbon emissions to the atmosphere, to reduce our impact on the climate. But I think at this point, we also are at the point where we really need to think about how do we become resilient to those changes? How do we prepare and adapt to those changes? And that's what I'm really aiming to talk with you about tonight. What are the consequences that we might face and experience? So I'll start off here with some just kind of basic, some background. And I put these 100 dots on the screen to help us think about this magical molecule that's floating around us called carbon dioxide that is at the heart of this problem. Of course, carbon dioxide is something that's really important and useful for us. We breathe it out. We depend on plants that photosynthesize from it, and it keeps the planet from freezing. But if you imagine if I grabbed in front of me 100 molecules out of the air, even just one of those, 1% of those would most likely not be a carbon dioxide molecule. That's because carbon dioxide is so rare in the atmosphere. It's kind of shockingly rare. But 78%, you probably all know this, 78% of the air around us is nitrogen. It's not a greenhouse gas. It doesn't affect the climate in a really significant direct way. The other 21% is oxygen, which we're so dependent on. It's also not a greenhouse gas, although it's important for establishing the ozone layer. But even that 1% is most likely argon. It's not carbon dioxide. Even if I collected 1,000 molecules here in front of me and just try to pick out one of them, most likely even just one out of 1,000 would not be carbon dioxide. I have to go to about 10,000 molecules, and maybe at that point I would grab 4. At this point, in the way our atmosphere has changed, about 4 out of 10,000 molecules might be carbon dioxide. So it's this incredibly rare trace gas. It's not significantly abundant in the atmosphere, and yet it totally defines Earth as we know it. So I just want to get us started here so we're all kind of familiar with the basics. Right now, that 4 out of 10,000 is also another way to think about it is that it's roughly 400 out of a million. So if I grab 1 million molecules here, and so the way we typically talk about atmospheric carbon dioxide levels is in parts per million, so the number per million. So right now we're at, when I checked it yesterday, we're at roughly about 422 parts per million. So 422 out of a million molecules right here are carbon dioxide. What's interesting though is that if we go back and think about this landscape in the past, during the last ice age, we know the climate here was different. You go up to Jenny Lake or any of like the other lakes like Bradley and Taggart, lots of places up in the Tetons, you can see the evidence of these glaciations that covered the mountains. The ice came all the way down from the top of Yellowstone all the way down to the southern edge of Jackson Lake. And that was in a world that was roughly 5 to 7 degrees Fahrenheit colder than where we were in the mid-20th century. So 5 to 7 degrees was enough to transform this landscape from one being covered by ice to kind of the landscape that's covered with forests, the way we think of it today. What's interesting to know is that the reason it was so much colder was for various natural reasons. Carbon dioxide was only about 180 parts per million. So this would again mean like only 1 to 2 of those molecules out of 10,000 would have been carbon dioxide. It's actually getting so low at that point that it even becomes a bit challenging for plants to photosynthesize. So that not very abundant, and so the greenhouse effect on the planet was very weak, and we cooled into this deep ice age about 18,000, 20,000 years ago. And it ended about 15,000 years ago when carbon dioxide started to naturally rise. And so I tried to sketch in here, sort of imagining the same, if you're looking up there from sort of Taggart Lake, the moraine there, you can see these big moraine, where the glaciers would have come down out of the canyons there. And of course, you have to imagine this without the trees and with a lot more snow, but this would have been roughly what it would have looked like. Over the next 5,000 years, carbon dioxide rose by about 80 parts per million. So it got up to about 260, so maybe 2 to 3 out of 10,000. And that raised the temperature enough to melt those glaciers away and leave behind the moraines and the big glacially carved valleys that we see on the landscapes. And I always think of this as like this landscape, you can go, some of you may have heard me say, if you've ever heard me talk before, that you could go to Egypt and stand on the ruins of the ancient Egyptian civilization, or go to the Parthenon in Athens and experience ancient Egyptian civilization, or go down to Guatemala and stand on the ruins of the ancient Mayan civilization. Here we are standing on the ruins, in some way, of an ancient colder climate. This whole landscape here is a whole story of climate change that was roughly 5 to 7 degrees warming that transformed this from a very glacial covered place to a place the way we all live it now. So I wanted to set that, so just keep in mind that ice age difference from today is about 5 to 7 degrees, and it's about 80, that included a rise of about 80 parts per million of carbon dioxide. By 1850, it had naturally risen up to about 280. And what's interesting is to watch what we've done since then. So I'll walk us through a little graph here, starting with the earliest measurements that were made in California and then eventually out in Hawaii of the amount of carbon dioxide in the atmosphere. And so, and I'll just sort of benchmark the history here using some important sort of geopolitical markers. We go back to October 17th, 1973. That was when OPEC imposed an oil embargo that was a major shock to our energy systems or the way we thought about energy, and lots of geopolitical context. And it happens, I picked that date, not totally arbitrarily, because it's also my birthday. So what you're about to see is how carbon dioxide has changed in my lifetime. So back when I was born, there were roughly 330 parts per million. By the time we get to the 1980s and the Berlin Wall fell, the end of the Cold War, again, another major change geopolitically, carbon dioxide had risen up to about 353. By September 11th, 2001, it had risen up to about 371. And since then, we've now come up to about 422. if on the slide, you can also see I've marked on there other important scientific reports that came out along the way, sort of warning us about the problem here. And so it's really interesting to think that in the time since we've known a lot about the science of this, the problem has just become much more intense. And so every time this CO2 ratchets up, it's like adding another layer of insulation to the atmosphere that's trapping heat. And just to put it in context again, that's roughly the magnitude of change that we've done in my lifetime is actually slightly larger than the change from the last ice age to the sort of pre-industrial levels. And so remember that natural increase of about 80 parts per million was enough to warm things about 5 to 7 degrees. And so we don't even need climate models or anything like that. We can just know from this history that adding the amount of carbon dioxide to the atmosphere that we've added today really poses a risk that we will warm the world by about as much as warming took place to end the last ice age. And think about all the transformations that went along with that. That's what we need to begin to grapple with and think about how will we face those same types of changes going forward. Here's another way to look at this. The biggest uncertainties about the future are not the science, the physics of how carbon dioxide traps heat, which we'll talk about in a second. The biggest uncertainties are how much more carbon we can put into the atmosphere. And so if you look at this graph up here, there's sort of two end members that or two different possibilities that I'll come back to a few times this evening. One is if we mitigate carbon to some degree, we can kind of keep it within not too much higher than where we are right now. But if we don't do much mitigation, we're ending up much higher, almost about 1,000 parts per million. So 10 out of 10,000 molecules. And that is nothing like, or just totally beyond, all of this is way beyond what the natural range of variation has been over, approximately the last million years. So last million years, we've gone in and out of ice ages as the amount of carbon dioxide fluctuated, and we are just rapidly moving away from that world. Yeah, go ahead. You have a question.
Were the fluctuations in the past and the rise of 80 just based on the glacial cycles? Like what caused that rise of 80?
Yeah, it's naturally. It's actually, we don't totally understand it, but it's some combination of the way Earth's orbit shifted slowly over tens of thousands of years, altered things like the amount of dust washing into the oceans, which fertilized the oceans and affected how much plankton living in the ocean drew carbon dioxide out of the ocean. So there are all kinds of natural processes that very slowly would shift the amount by those 80 parts per million. And it seemed to cycle in and out here. And the reason there were cycles is because it's in sync with these orbital changes to Earth's orbit that take 20 to 100,000 years. So much slower than this big increase that we've added now. And honestly, that's actually still a puzzle that people are spending quite a bit of time on, is really trying to understand why it did this. But we know that the carbon dioxide was really essential to driving those ice ages. Okay, so I have another quiz for you. This time it's not a survey, it's a quiz. I'm a professor after all. If you need the link, it's here, but you should be able to just go back to the survey tool that you used before. And I have the question for you. It's a multiple choice. Not all of these answers are correct. Why do greenhouse gases warm the Earth? And there's sort of three options. Here, I'm going to give you three options. The first one is greenhouse gases warm the Earth because they trap additional energy coming from the sun. Second one is going to be they warm the Earth because they vibrate and stretch and bend and rotate. And the third one is that they warm the Earth because they trap heat that's escaping from the surface, going back out to space. So, okay, so raise your hand if you think they trap more sunlight, and that's why they warm the Earth. Okay, don't be afraid. It's all right. All right, how about, I didn't get a lot of takers on that one. How about you, because they vibrate and they bend and they rotate. Still not getting a lot of takers here. Okay. And finally, they trap heat that's escaping out from the surface. Okay, good. That's generally the right answer. The second one is also true because the way in which they trap heat that's going out from the surface is they get energized by bending, stretching, rotating. So I'm going to challenge you to stand up with me, and I'm going to teach you how these molecules work. We're going to do a little greenhouse gas warming yoga here. Okay, so we're all going to be carbon dioxide or water molecules. Water is also a greenhouse gas. So imagine that it's CO2. So like your head is the carbon, and your fists are the oxygens, and your arms are the bonds between these. So there's 4 ways that these, or you could be water, H2O. So you could be an oxygen with 2 hydrogens as your fists. The way that these capture heat is that as wavelengths of infrared energy, heat, escape from the Earth, they hit these molecules, and certain wavelengths, some of them cause the bonds to stretch like this. So everybody do this. This is your exercise for the evening. This is called asymmetric bond stretching. It happens at about 2.6 microns. So that's the wavelength that it absorbs. At 2.7, they do this. They do asymmetric, or sorry, the first one was asymmetric. This one is symmetric bond stretching. Then as we get up to about 4 for carbon dioxide, we start bending. Oh, sorry, I'm blurring my things here. Carbon dioxide does not do all these. Water does all of them. Well, carbon dioxide does not bend that much, but water bends. So, and you can imagine water is like doing this and bending at the same time. And then finally, at longer wavelengths, they rotate. They can rotate this way, you can do somersaults. There's various ways they rotate. And all of these things, these are the ways that the molecules trap the heat in the atmosphere. So I just wanted to do that so you at least can try to remember the physical basis behind this that we've known since the 1850s or so.
Just have to advance it in mentimeter. We hear what's embedded.
Okay, that's strange.
Maybe if you want to finish it, that's fine, but that's the answer.
Okay, I'll all right. I'll for the next one, I'll try it. Okay, so just to give you a demonstration of this, sunlight goes past these molecules and is very short wavelengths, very energetic. But it doesn't cause the bonds to bend or stretch or rotate. But I'll go back and do this again. So the sunlight comes by it, but the heat on its way out goes up and it gets absorbed by these molecules and bends and stretches, and that's how it gets trapped. And often when that molecules then re-radiate that energy back, it comes back towards the surface. And so we actually get warmed at the surface. Even though there's only 4 molecules out of 10,000 in the atmosphere that are CO2, we're getting more heat from those than we actually are getting from direct sunlight, which is interesting. And it turns out that this has been trapping a significant amount of heat. Do you have a question? Which mode? Oh yeah, so the most important one for carbon dioxide is the bending, but the most important one overall, it turns out to be the rotation of water molecules. And so you think about this, you start adding CO2 to the atmosphere, make the atmosphere a little bit warmer. That causes more water to evaporate out of the ocean. And that water then becomes an additional greenhouse gas that makes it even more intense. And it turns out that the place that the Earth is absorbing all this heat ultimately is not the atmosphere. It gets radiated back to the surface and it gets trapped in the oceans. So this is a plot from 1955 into 2015. I haven't totally updated it here, but the trend continues. For the first part of the time where we had measurements of the heat content of the ocean, it kind of bounced around some sort of average value there for several decades. But beginning in the 1980s, the amount of CO2 in the atmosphere got high enough that we really started absorbing a lot of additional heat into the ocean. And so the heat content of the ocean has been rising. And I know now everyone's probably used to thinking in the energy units of joules per year. And there's 10 to the 21st joules per year. So that's 10 with 21 zeros after it, joules per year. A joule is equal to 1 watt per second. So your light bulb that has 100 watts, it would be something like 100 joules. And for comparison, This is putting out 10 to the 21st joules per year. That's how much is being absorbed in the ocean. Here's the amount of total global electricity production that we do. It's 10 to the 19th, so 10 with 19 zeros after it. And if you're not used to thinking in these terms, this number is roughly, in really round numbers, 100 times smaller than the amount of heat we're absorbing. So I always think of this as like, if we wanted to heat the ocean, we were doing an awesome job at it. Because instead of like putting all of 100 more power plants for every one that we have on Earth and putting all the energy into the ocean to heat it up, we're getting electricity and while we're getting the bonus of heating the ocean. Of course, that's not the way we like to think about it, but the ocean is trapping a massive amount of heat. And you can think about this as it's the pot of water that's slowly warming up on the stove. This has been really beneficial to us because all that heat that's going to the ocean is not going in the atmosphere. This is actually helping to keep the rate of warming of the atmosphere down. It's like a big swamp cooler. But slowly over time, as the ocean warms, it will start re-releasing heat back to the atmosphere. And so if you look at various projections globally, there's a lot of different models, a lot of different groups around the world that have simulated how this will play out. And this is kind of a summary of how the amount of warming might play out from their perspective. We're likely to reach about 1.5 degrees Celsius or 2.7 degrees Fahrenheit of additional warming sometime between now and 2043. We'll get to the point of having about 3.6 degrees Fahrenheit or 2 degrees Celsius sometime between 2031 and 2059. So definitely by the time we're in mid-century. And then we'll reach 3 degrees Celsius, about 5.4 degrees Fahrenheit, about 2039 to 2080. It starts to get more uncertain the further we go out in time because we're uncertain about when we're going to release all this carbon or how much we'll release. But potentially by 2056 to 2084, we might get to 4 degrees Celsius or 7.2 degrees Fahrenheit. And remember, that last ice age was 5 to 7 degrees Fahrenheit colder than today. So we're talking about the transition, the difference in the climate between now and the last ice age happening between now and roughly 2084. Yeah.
I have an ice age question for you.
Sure.
Before we get too far away from that.
Yeah.
Now, I gotta qualify this. I read a book a while ago. I think it's still on my bookshelf. Don't remember the name. It was something like The Coming Nuclear Winter or some crazy name like that. But basically, the thing that really struck me in the book was it indicated that some of the ice ages that occurred millions of years ago happened during periods of much higher CO2 parts per million in our atmosphere, like maybe 7 times higher than today. How could an ice age occur under those circumstances, or was it just totally bullshit that I read?
I think it's just that we haven't fully figured out the history of carbon dioxide in the atmosphere at the time when that book was written. It's become increasingly clear that the history of ice ages on Earth is almost always, there's ice and expanding ice ages whenever carbon dioxide gets below about 500 parts per million. If it gets above 500 parts per million, you basically have an ice-free world. And we know this because the last, 1 to 3 million years was a pretty significant ice age period, and CO2 has been quite low during that time. About 300 million years ago, there was also another period of time where there was a major glaciation in the southern hemisphere, and that was also a period of very low carbon dioxide. And then there were, if you go back to 600, 700 million years ago, there were actually a couple time periods where the planet almost seemed to have entirely frozen over. And those are also time periods of exceptionally low CO2. And there's been a massive amount of work to really refine our understanding of that history because of this question exactly. It does seem at first like there might be a mismatch, but they seem to line up quite well. Yeah.
I mean, for the background of this, so you know what the CO2 was 300 million years ago because of the gas bubbles?
Yeah, so we know directly for the last million years, or roughly the last million years, you have ice bubbles in Antarctic ice sheets that you can measure. Beyond that, what we have to do is use various geochemical measurements that are preserved in rocks. And it turns out that there are some things like the way boron isotopes change in the skeletal remains of plankton in the ocean that actually really carefully track the amount of CO2 in the atmosphere. And it's because the amount of CO2 in the atmosphere affects the pH of the ocean water, and that affects how these boron get into these shells. So people have cross-calibrated these things to be able to take us much, much deeper into time. But of course, it does get more uncertain. The other part is it also makes sense when we see these ice ages, because we know that naturally, one of the things that causes CO2 to go down is when we have big mountain building events. I won't go totally into the details here, but basically every time you build a big mountain, you start stripping CO2 out of the atmosphere as you erode those mountains away. And so we have had ice ages when we built the Himalaya. That's what led to sort of the most recent one. In the 300 million years ago, was essentially a consequence of the Appalachian Mountains being eroded. And it's a different story for these big snowball episodes when the whole planet got covered, but it's really interesting and geologists have been really fascinated with this because it's such an interesting way to try to better understand this. All right. So I want to shift gears from that bigger global perspective to talk about what's happening here. What's going on now in Jackson? And you might be aware that if you went and looked at the temperature data from the Jackson weather station, there's not really a very clear warming signal here. So what's going on? This is the daytime maximum, like the daytime temperatures from about 1920 up to today for the weather station here in town. And I've subtracted out the average. So these are just the departures from average. And you see some years tend to be about 2 degrees, up to 2 degrees Fahrenheit warmer than average. Some years are 2 degrees colder. And we've had a string of colder daytimes in the last decade or so. Now, this might seem surprising, but it's also the case that it's not really happening everywhere. That pattern is pretty distinctive, like most intense here in Jackson. Even if you go look at the weather station from Moose, it's not quite as clear. However, if we take all the weather stations in the region here, Moraine, Driggs, Alta, Bondurant, Dubois, over in the Darwin Ranch, Pinedale, up at Snake River on the north end of Jackson Lake, none of these show particularly strong warming. You can see there's actually a bunch of high temperatures here in the 1930s. And then since then, temperatures have generally been lower and you don't see a lot of warming. This might seem surprising, but oh no, what happened? Oh, okay. But it turns out it's different in the daytime versus at night. So if we look at all those same stations in the nighttime and look at their minimum temperatures, what we see is that almost all of them have even the Jackson one that shows this cooling of daytime temperatures recently, have had strings of above average nighttime temperatures for the last several decades. In fact, we have kind of a gap here in the number of years where we have had cold nighttime temperatures. And this makes sense because what greenhouse gases are doing, remember, is trapping heat and preventing it from escaping into space. And nighttime is like our drafty window. We don't have sunlight coming in, warming things up. It's the time when we lose most of our heat to space. So as we've been adding these greenhouse gases, we've been slowing the rate at which heat escapes from us at night. And that's not trivial, it's actually quite important. Think about in the spring when the snow is melting. If the temperatures get cold, the snow will refreeze and last longer. If the nighttime temperatures stay high, the snow will begin to melt faster and faster because it warms up and it doesn't have that chance to refreeze. Likewise, now going into the fall, as we get into fire season, typically the way fires end is that we get frost or snow that's really falling on those fires to help to put them out. But if you don't have the nighttime temperatures that cool things off, you don't necessarily get that frost, or you don't get the dew even that might keep some of your fuels moist. And so the warm night times can actually extend the fire season. So the change in nighttime temperature is actually a very important driver for some of the changes that we're going to experience. And this is a pattern that we see not just in this region, but kind of from here eastward across eastern, all the way to the eastern part of the US. Daytime temperatures have not changed very much, but it's nighttime temperatures that have been warming. Elsewhere in the world, both day and night have generally been going up. But for various reasons here, our daytime temperatures have stayed pretty flat, but all the warming we're experiencing is primarily at night. And so And just to show you, like, if you look all across the state, this animation here is all the different weather stations across the state of Wyoming, kind of one after the other highlighted. I'll try to go back, play it again. So you can see like very cold places like Yellowstone Lake down here at the bottom, up to the warmest places like Cody at the top. And while Jackson, is one weather station that shows this nighttime warming, it's not just Jackson, and we're not reliant on any one station. We see this as a pattern across the whole region. And you can kind of think of this as each of these gray lines is a different weather station. I just was trying to plot them all together. And you can kind of see the cloud of temperatures here was, if we ignore the very coldest sites, went from about 24 degrees up to about 34 degrees at the beginning of the 20th century. And that cloud has slowly moved up by roughly 2 degrees Fahrenheit. So now the temperature ranges from 26 up to about 35 or 36. Yeah.
Can you explain those charts in relation to the one that's on the fact sheet?
Yeah.
Is that just averaging out like
Yes.
time and nighttime?
Yeah, so in fact, here it is. This is basically the same thing that's on this chart here. But this is just the temperatures. If we average all the weather stations around the Yellowstone region from 1950 forward, we see this about 2.3 degree Fahrenheit warming. And this is averaging, this is the average temperature, which means we have that like lack of change in the daytime is being counteracted by the fact that the nighttime is warming. And when you average those together, you get this mean warming of about 2 degrees Fahrenheit. Interestingly, that's very similar to the global trends. So here, this is NASA's estimate from 1900 up to 2020, actually 2023 of global warming. So roughly here's the difference from the mid 20th century as 0. And we see this upward trend in the black line there. And here's the Jackson daytime temperatures in the orange aren't really going up as nearly as much. But if you look at the blue, which is the nighttime temperatures, they're actually going up about 1.3 times or like a third as fast as the global average. But when you put those two together, the sort of lack of warming in the daytime and the increased warming at night, they kind of average out to be roughly the same as the global rate of warming. Interestingly, this is actually relatively slow compared to a lot of the rest of the West. I just put Salt Lake City here as another example. But Salt Lake City, if you look at its average temperatures, they're going up about 1.6 times, so like roughly 60% faster than the global average, and almost double actually the rate of warming here. So this is an interesting issue to consider, is that the Jackson Hole region is warming, but it might not be warming as fast as other parts of the West, which might make it kind of a refuge for escaping that heat elsewhere, especially because we're also up higher and it's cooler. And so this is a factor to consider in some of the indirect consequences that we might experience. Okay, so here's this is now 1900 out to 2100, and the black line is kind of the data, the average for this region again, and here's where we are now. And these red and blue lines represent two possible futures. The blue is where we manage carbon and keep it close, relatively close to the level at which it is now. And the red is if we don't manage it. We have some choices before us. If we mitigate, it warms up by about 7 degrees Fahrenheit. If we don't, we end up warming about 13 degrees on average. And remember, a really important thing here is it's not just the absolute amount of warming that matters, it actually is how long it takes us to get to some of those points. So if we look at like 6 degrees Fahrenheit as a threshold, if we don't mitigate carbon emissions in the future, we get there by about 2060. But if we do mitigate substantially, it takes until 2100. So we get an additional 40 years to adapt and plan for it. And of course, it actually doesn't matter in the near term what we do. In either case, the warming over the next 30 years or so is roughly the same. It only starts to become different later on. So this is one of those weird things where we have to take action now in order to have consequences that matter 30 or more years into the future, which has been one of the biggest challenges here. Yeah.
Is that based on just natural processes causing it to drive, or is that taking into account increases over time? Carbon dioxide?
Yeah, so this is taking into account the natural, or like, the natural variation is the bouncing around year to year. We're rolling dice, some years is warm, some years is cold, but the trend upward is because we're adding significant amounts of carbon
Is that
dioxide.
assuming continued outputs by humans?
Yes, it does assume continued. It-
Increasing.
This assumes that we continue to put carbon dioxide in the atmosphere at the rate that we're doing now. Whereas the blue line assumes that we level that off. Something you may or may not know is that we're still increasing the amount we're adding every year. So it's not just that we're adding a fixed amount every year and it's going up. We're actually adding more and more and more every year. And so if you continue that trajectory, you get the red line. If you start to level that off or even bring it down, that's how we get to the blue line. But both of these, the warming is a function of our activity, but we have a choice between 7 degrees or 13 degrees by managing that. Yeah,
If you were able to draw our input of carbon down.
Yeah.
Another line.
yes. So there is some possibility, if we could really bring it down, that we would level this out. But that is something we have not quite gotten on board with yet. Yeah. Yeah.
So, I have some ideas, but what is the reason for more and more and more and more?
Yeah, there's multiple pieces to this. Basically, on some fundamental level, it's the growth of the global population times the growth of our energy consumption per person. So as the world becomes more and more it's often very far away from American levels of consumption, but as it gets closer to that, everyone is starting to use more energy and put more carbon to the atmosphere at the same time as the population is growing. It's particularly true for the US. So we've substantially increased our energy demands. I mean, right now, the biggest thing that's just impacting us is going to using AI. All these AI tools, like a single AI computer farm can take up as much energy as a small city. And so the amount of carbon emissions tied to that, technological revolution, is tremendous.
Get Bitcoin, which is worthless.
Yeah, well, exactly. All of these things that are using a lot of computing right now are something that is contributing substantially to this acceleration. So it's not just the number of people that's growing, but per person, we're all now potentially using AI tools that we weren't using 5 years ago, and so that's added all this additional carbon to our personal use. So I don't want to forget to say, 7 degrees here again is the difference between last ice age and today. So we're talking about either doing that level of change or maybe doubling that. Oh, I guess I had it in there twice to say that. Okay, so all of this is why I think it's really important to think these are the changes that are happening. They're already begun here. And it's really important at this point, we've committed to so much of this continued warming going forward that we not only need to make those choices about how we manage the amount of carbon going in the atmosphere, we also have to begin to prepare for the impacts. Because even with some mitigation, which is likely, we're still talking potentially about an ice age level of impact on our ecosystems. And so that's why it's a really important thing to start looking ahead towards is how do we plan for that? Okay, now we'll see if Menti is my friend. I don't know. Oh, come on. Maybe not. Yeah, I've got to go into Menti, which I think is here. Oh, what? Oh no. I was so worried about that. They told me that if you're in the middle of a live presentation, we won't cut you off. Oh no. Darn. Okay. Continue with free, but that will, I think, not let me continue with the, let's see what happens. Oh no, darn. Oh my gosh. I'll go back. I think we're gonna be out of luck here. Okay, we're gonna do this another way. That's what the no cards were for. We wanted to back up, yeah.
So you're saying with mitigation, we're gonna reach potentially the next ice age in 30 years.
The opposite.
Yeah, but like, if you think about the amount of warming since the last ice age, that melted on the ocean way. It's roughly that amount. Now, that doesn't mean we will feel like the impacts right away, because think about, again, putting a pot of water on the stove. It will take a while for that water to warm up and boil. So things are not gonna change immediately, but the temperature is likely to be in that range. And again, the interesting thing about that is, remember that temperatures here have been warming so far at roughly the rate that the globe is warming. And that rate is basically spot on with the projections that were made as early as 1981. So we're really warming at the rate that the models anticipate. And so there's a lot of reason to think that we would need to continue to warm at that rate. Okay, so I'm gonna do this a little bit with show of hands. Here's some things that I'm prepared to talk about. And so I'll just go down the list, and you can raise your hand. Feel free to raise your hand more than once. We'll try to rank things, and we'll jump around to topics you want to hear about. So one is, I talked about temperature. You might want to know what else has changed, like precipitation, snow, stream flow, all those things. We could spend some time looking at the other changes. I'll go through the list and I'll ask you to vote. The next question is more about what will you actually experience? If you talk about warming, the ice age amount of warming in the next 30 years, what will that really mean for you on the ground? I think that's an interesting thing to consider. The third point is, what's the future of our snow? We talk about warming that much. You can imagine there's a risk to our snowpack. How will our rivers and streams change? What about wildfire risk? And then of course, we could also talk more about the science here. Is it really CO2? How certain are we that it's CO2 and not something else? And how certain are we about the projections? Projections. You know, how certain are we, like, what is the uncertainties related to the models? And we can of course talk on other topics as well. But these are some that I thought we could start out with. So I'll ask you to raise your hand if you're interested in like thinking about what else has already changed. You want to spend some time on the precipitation or snow or stream flow changes? Okay, got a hand, some. Okay, I'll try to do this without having action now. How about what will you notice in the future? Like what will you experience? Okay, a lot more interest for that one. How about the future of our snow? Okay, also a key topic, right? How will our rivers and streams change? Okay, good. Lots of takers for all of these. How about wildfire risk? Do you keep going? Yeah, all right, good. How about, do you want to know more about CO2? Okay, covered that. How uncertain are we about the projections? Okay, we'll try to get to some of those topics as well. All right, so let's jump ahead here to what will you really notice or experience? And that will be a natural segue actually to the snow question as well. So I'm going to go out of this for a second here. Oh, whoops, I forgot to switch this around. I appreciate everyone hanging in there for the experiment of doing this for the technology. Yes.
Based on what you're telling us,
Yeah.
is planet Earth done with ice ages?
Oh, yeah, really good question. We do think we are likely to skip the next natural cycle. Right now we would be logically headed into very slowly over 20,000 years or longer. We'd be slowly headed into an ice age. And you may have heard sometimes people say, well, back in the 70s, scientists said that we're headed into an ice age. And that's because that's when they figured out the cyclicity of the ice ages. And we are on track with that. But we've added so much CO2 that we are saving ourselves from that whole phase. So yeah, that's a good point. We really have changed the trajectory of the planet's climate. Okay, so things have wait, oops, sorry, I hit the wrong one here. We want to talk about what will you experience? Okay, so one of the first things you might imagine, yeah,
Just make one caveat. It always bothers me, I read a lot of science fiction. The planet is going to be fine. This is a ridiculous discussion. The discussion has to do with the ability of Homo sapiens to habitate this planet. And that is not going to last very long, no matter what. we do. And so when people say, the planet does great over millions, and we're the problem.
I'm not worried about the planet at all.
We're the
The
problem.
planet has been much warmer than this in the past. It's just that we've built all of our infrastructure, all of our agriculture, all the things we depend on around the climate as we know it. And so you're right, the risk is to us. I mean, we will impact other species for sure.
We killed them all already.
Yeah, this is a really good point. There's a lot of other things we're going to challenge it. But let's talk about things that you're likely to experience. So again, the blue and the red here are kind of, I'll show in some of these graphs, I'll have these two things that represent how things might change if we have some mitigation of carbon, which is the blue, or if we don't, we have no mitigation, which is the red. And this particular plot, which comes from the Greater Yellowstone Climate Assessment, which you can find online if you want to look at it, gyclimate.org. This is roughly the number of days below freezing, the average temperature below freezing, Jackson. So, you all know that we're closer to 250 days a year where the temperatures are quite cold. But as we go forward in time, as things warm up, that, not surprisingly, the number of days that will be below freezing will go down. And it goes down, roughly to about 180 by the end of the century if we mitigate, and maybe down to about 150. And so if you think about that, that's several months worth of like warmer than freezing temperatures that we're going to have. So if you want to grow your tomatoes here, it's going to get better. So there are some upsides, but again, this is the hint that there's going to be impacts to the snow, right? Because the snow depends on the temperature below freezing. And again, if we look out to mid-century, we're getting down to about 200 days per year. And again, coming down from about 240. So we're talking about a month less freezing weather, even by mid-century. And then it starts to get more extreme if we don't mitigate after that. The flip side of this is days above 90. So those are quite rare here. They only happen occasionally. But with these two options, with some mitigation, we end up with roughly about 2 weeks of 90-degree weather here by the end of the century. But without any mitigation, we end up with 2 months of 90-degree weather by the end of the century. So you fundamentally imagine how summers here would be completely different if you started having these big strings of temperatures above 90 degrees. Something that we just really don't experience very often now is something that would become the norm as part of our summers. And so by mid-century, in the next 30 years or so, that starts to creep up to about a week or so of 90-degree weather. And that feels like something that's fairly certain because it doesn't really matter what we do with our carbon emissions. Both tracks end up getting us to that. Here's another thing that I think is really interesting. I'll show you this little video here of a heavy rainfall that I drove through recently. You can see all the flash flood coming down the street. This is where, going back to that point, if our infrastructure is built for the climate the way it used to be, one of the big issues now is that as the air gets warmer, it can hold more water. The warmer it gets, it's basically the bigger the sponge is, the air is full of moisture, the air can hold. And so as we go out to 2 degrees Celsius, 3 degrees Celsius, 4 degrees Celsius, the range of single day precipitation events gets bigger and bigger and bigger. So right now, this is for the sort of statewide average actually. And like if you looked over like the last 30 years, our wettest days, our heaviest rainfall would be somewhere between like 3/4 of an inch of rain up to about a little bit more than 1.5 inches of rain. And this is the sort of typical range. The heaviest rainfall in Jackson, or heaviest precipitation event in Jackson, was in March 1995. And that was about 1.8 inches of precipitation of water. And that becomes closer to part of the normal range of possible heavy rainfalls that we start to get if we get out to temperatures being up around 7 degrees Fahrenheit warmer than today. Which again, could happen by mid-century, depending on how fast we control the carbon emissions. So the thing to look at here is just how heavy rainfall is. On the low end, it doesn't change very much, but on the high end, we just start getting more and more intense rainfall or snowfall events. And so if you're building something with a culvert, think about building a bigger culvert than you're planning. You're gonna need a bigger culvert. But there's an interesting twist to this. Like when it rains or snows, it could be much heavier in the future, which seems like a counterintuitive thing. The world's getting warmer, but we might have heavier snowfall. But that's because the air in the winter can now hold more moisture. So even if the temperature has warmed up from, say, 10 degrees to 20 degrees, it now also has more water, so that snow when it falls could be heavier, which is great for certain things, of course. But the flip side of this is that there's also expected to be longer strings of days between precipitation events. So this is just a map that sort of shows this, where it's brown on the map. This is for 2 degrees Celsius warming, 3 degrees Celsius warming, or 4 degrees globally. Where it's brown, we have increasing numbers of days where you have consecutive dry days in a row. So we have this strange combination possible where when it does precipitate much more heavily, but then you have longer time periods where it doesn't rain or snow at all. And so it can get up as you start to warm things up here. Interestingly, it's different if you go out into Idaho. It actually goes in the other direction. You actually start having fewer dry days there because atmospheric river events start coming into the mid-continent. And we're kind of on the edge here. Between the place where it flips over, but for Jackson, it is likely that we will increase the number of days without, like strings of days without precipitation. And I want to also point out there's an interesting twist that we've been intrigued by. Oh, go ahead.
So over the year then, is there more rain or less rain?
Yes, exactly. Yeah, it's really interesting. Overall, we actually think maybe there's a slight increase in total precipitation, but a substantial shift from rain to snow, or from snow to rain. The other thing is it's actually shifting when it occurs during the year. So both the winter and the summer right now have had reductions in precipitation, but spring and fall both had increases. So there's this shift in when precipitation has occurred. So it's not as simple as just like, is it gonna be drier or wetter? We have this weird combination of more rainfall and faster melting of snow in the spring, which can increase flood risk, but then less rainfall and earlier snowmelt. That means all the water is flushed out of the system earlier, so that by the end of the summer it could be really dry. So we have both increased flood risk and increased late snow risk, which challenges that. Like it's not just one or the other. Yeah.
So I have a question about the information that you're getting so that I can understand how to better trust and rely on different sources.
Yeah.
So there's different models giving you different information. So how do you know which models to trust?
Yeah.
And are the models agreeing on the information you're showing us, or are they not agreeing?
That's a really great question. Let me go back to one of these projections here. Okay, so see this, the graph here. The red line here is the average of about 30 different models. So you have groups in Germany, at NASA, at Princeton, in the UK, in China, all these different groups around the world that have built climate models. And an important thing to know about the climate model is it's just based on the physical principles of how the atmosphere should work. You're not feeding it data. You're just saying, okay, but if you add CO2 to the atmosphere, how much heat should it trap? And so all these different groups basically have the same equations in their models, but they implement it computationally slightly differently. And the pink span here is the range of differences between those 30 models or so. So in general, they all agree that there's this upward tick, like in this case, in 90-degree days. Whether it's 20 degrees or 20 days or 60 days, that's the difference between what the models are saying. but they all agree about the same direction. So that's one of the reasons to focus on some of these things. There's generally a same tendency, sort of like, you know, if you look at weather models and they're all projecting that a hurricane is going to hit Florida. Instead of at some point early on, some might go offshore, some might go to the Gulf of Mexico. In this case, they're all sort of aiming that hurricane, in this case of 90-degree weather, you know, here. And it's just, there's differences in the intensity of it. So there is uncertainty, but in general, these are things where the models agree. The other thing, and I'll show you, I have a slide to talk about this. Find it. This is just from one climate model, the NCAR National Center for Atmospheric Research model that's run on the supercomputer down in Cheyenne. And this is what they did. Instead of projecting the future, they tried to run backwards to the last ice age. So they're going back here 11,000 years. So this is 11,000 years ago to present. And there's a kind of gray line in here is the model. And it knows nothing about the data that we have of observations about the past. It just knows like how much CO2 is in the atmosphere, how Earth's orbit has changed, just some of the basic physical parameters of the climate system. And then the pink bar there is the best estimates we have from like hundreds of locations where we have estimates of the temperature of this time period. And so in this case, it gives a lot of confidence that the models are actually capturing climate trends very much the way we would expect them to. I'll also say, this is also my chance to tell you, you can all make an accurate climate forecast right now. So if I asked you to tell me the weather exactly next week, how many people would feel confident to say that? Not many, right? Like a week from now, it'd be hard to know what the weather is going to be, because it's hard to know, like, is a single storm going to north of us, south of us? Are we going to get hit by a heat wave? Is it going to be a cold outbreak from the north? It's very chaotic. But what if I asked you, is it going to be cold next winter? Or is it going to be warm next summer? I think we'd all feel confident that we'll say that next summer is going to be warmer than this coming winter. And the reason for that is the basic physics of the way the climate system works. We get more sunlight in the summer than we do in the winter. And so oddly, it's actually easier to make climate projections because you're projecting that kind of general sense of the weather rather than the specific weather you're experiencing. You're predicting like what's the general range of precipitation you might get, not exactly what precipitation you get on a good day. And so that's in some ways, that's why we feel more confident in the climate models. Yeah. Believe it or not, Harriet Hagerman invited me once to Cheyenne to speak about this exactly. And I had lunch with her and I spoke to a whole bunch of people in Cheyenne. We did talk about it and it was a great conversation. Yeah, that was about 10 years ago. But yeah, it happens. I mean, it's I think there is increasingly across many sectors of our state, of our nation, recognition that something's changing and we have to be prepared for it. Whether you want to assign it to human activity and go down that road or not is different from just planning, not burying our head in the sand and looking ahead and seeing like things are changing and we have to, regardless of whether we want to manage that carbon or not, we need to be prepared for what those outcomes are. And it's not just, and you can also think of this on the like energy industry side. We have made a lot of money in the state over time from fossil fuels, of course. But if we don't pay attention to this science, we might continue down that road, even though the rest of the world will stop buying those fuels from us. And so for our own economic reasons, we also need to pay attention to this because it influences the decisions other people are going to make that connect to our economic stakes. So I think there is, whether people always want to talk about it in a really public way or not, I think there is increasingly interest in considerations.
Right.
Yeah.
Has anybody ever asked you the question, will the number of ski days?
Yeah.
Jackson Hole be reduced?
It's a great question, Kay, and let me I so that's the other thing of that what will we experience that I should move us on to here is snow. And since we're a 6:45, this is a good sort of thing to wrap up on. Okay, so Jackson, of course, is famous for its snowpack. And it's a really essential water supply, as many of you know, to say farmers in Idaho. It's also, I mean, of course, it's locally important water supply, all that snow, but it's also significant for lots of recreation that drives the winter economy here. So how might that change? Oops. So this is looking at how average winter precipitation might change by mid-century. So this is kind of the average for 2031 out to 2060. And this is a map. So the black outline here is the Greater Yellowstone ecosystem. So here's the Wind River Range, here's Yellowstone Lake, here's Jackson Lake, here's Jackson, Driggs, Afton. And if you look at this, it's blue. And so in general, we're actually talking about a slight increase in winter precipitation over this time period. We expect there to be a modest increase in the amount of winter precipitation, but that's not the whole story. If we look at it in terms of the amount that is as snow that ends up on the ground April 1st, our snow water equivalent, the amount of water our snowpack equals on April 1st, here's an animation that shows how that changes. So we're going to start in 1981, and we'll look at every year going forward out to the end of to the mid-century. And you'll see year to year, there'll be differences. There'll be some really wet years where everything will look blue, see really dry years where the snowpack was low and everything will look brown. But overall, what you'll see is this tendency for it to get more and more brown. Of course, you always still might have some heavy snow years, but you just increasingly get years because it gets warmer and you have fewer and fewer of those days below freezing. Where you end up here in 2060 with a significantly reduced snowpack. And I think it's something important. Oh, come on, there we go. Something that's important to notice, it's not uniform everywhere. In fact, it's more intense over on the Idaho side. And that's because you actually start getting in the simulation thing, you start getting more rain on snow events that help to melt that snow faster. And of course, they're on kind of the upwind side of that precipitation coming up the Snake River Plain, coming from the Pacific. It's also lower elevation in many of those spots, so it's melting faster. Another thing that it's worth knowing is that since 1950, if you take all the weather stations around the Greater Yellowstone region, back in 1950, we had on average about 100 inches of snow per winter. That has now come down by about 24 inches. So we've had a roughly 24% reduction in the amount of snowfall across the region. And it's not in midwinter, it's the edges of the seasons. Like I was thinking about today, driving here, it was raining. You think, I can remember it wasn't that long ago where I was with a bunch of people who would always have a pool, a bet on what's going to be the first snow of the year. And often it was mid-September, September 15th, September 16th would be a prime date to choose. But we're not there anymore. In fact, September snow has declined by 93% since 1950. So this is, in some ways, you see this as total reduction in snow, but it's actually, it's also a shortening of that snow season. There are some interesting twists to this. If you go up higher in elevation, you actually sometimes get more snow. Like some of the weather stations that are up higher in elevation near here actually have had like a 200% increase in snowfall, even though on average, the whole region has had a decline. Yeah.
I think I've heard something similar to that, if you want to think of Jackson Hole Mountain Resort, they need more ski runs at the higher elevation, and it's where their lifts are that start going to be problematic.
Yeah. So let me show it from this perspective. This is another map, and it's showing where it's blue. Throughout the winter, you get consistent snowfall. Where it starts to get the red, orange colors, you get a mix of snow and rain. And when it's green, it's predominantly rain. We go back. So this is kind of where we're headed over the next 20 years or so. But by 2040, 2060, kind of mid-century, that pure snow zone starts to move up the slope. And by 2060 to 2080, it's really only at very high elevations. So you see this shrinking of that place where you can consistently rely on the winter snowfall. Look at that a different way. Here it is by elevation for this region. So the blue-red line here, oops. The blue-red line here is the snow rain line. And so, now it's down in town or lower through most of the winter. And again, this is averaging over the whole winter, so it includes the shoulder seasons. But as we move forward to kind of the next 20 years or so, that snow rain line starts to become on average above Snow King. Then by 2060 or so, 2070, it starts to get above Teton Pass. This is the scenario with some climate mitigation. In this case, we keep the snow we still get consistent snow at the top of the Jackson Hole Resort. But if we don't mitigate carbon, we lose that too. And also notice we cross these other key locations earlier in time because things just warm faster. Over the next 20 to 30, 40 years, it's basically the same. The greatest risk is to right here in town, like Snow King, because it's lower. But as we go forward in time, if we don't mitigate carbon, it just gets more and more threatening, even to the very high elevations. And so this is, so if you think about consequences for like cross-country skiing could be much greater, down low in flat areas where we do a lot of Nordic skiing versus the high elevation downhill skiing, which could be different.
Sorry, I missed
Yeah.
that. The red is what?
The red is where you have some percentage of the winter is falling as rain. So, and where it's green, it's all rain, basically, all winter. The red shades are some mix of rain and snow. But you start to get that rain snow mix coming up to these higher elevations. Yeah.
So I was just in Laramie this past weekend. I heard Professor Marat and David speak, among other things, about how climate was one of the big things that convinced her that while she continues doing her academic work, she also wanted to run for office, also commissions and things of that nature. So I guess my question for you is, what's your take on the role that academics are currently playing and could or should be playing in translating this research into action?
Yeah, I think that's a great question. My personal view of this is that academia is a great place to be the honest brokers about information so people can plan ahead. I could spend a lot of time getting more involved in some action on this because I feel motivated to do it. But I also but I realize there's a niche for me as a college professor and a researcher to try to provide the most accurate information we can. So we really have the information we need to make those decisions. And hopefully that dovetails with people making decisions that allow us to plan for this and adapt to it and make those choices about how much we want to mitigate carbon in the future. So my intention here, and I think our whole team's intention is to play that kind of honest broker role. But yeah, I mean, absolutely, Marab is a great example of someone who's decided, for her, the way to go forward is to get much more politically involved. Yeah. Yeah.
I want to ask you about the projections. One of the things that you had up there to talk about, everything I've read and lectures I've listened to, and that our projections are way off and things are accelerating, that they're way underestimates by and large. And the one thing I worry about is that it gets kind of the wrong, we understate the danger that we're in here because we're talking about we're talking about a fraction of a degree here and there.
Yeah.
And this accelerating nature and the fact that we've underestimated with all the projections, all the best scientists have underestimated, and they're very worried about that.
I think there is a credible case, I would say, from in fact, what I'm showing you here is a graph from a paper by Jim Hansen. Some of you might know Jim Hansen. He's famous for testifying in 1988 before Congress for the committee that Al Gore was the head of, that really got climate change into the public eye. And it happened to be that he was testifying, representing what NASA knew about climate change at the same time, same summer as the Yellowstone fires were going on. So you have this sort of reinforcing story of wildfire out here. And it was a very hot summer in the east in DC. He has remained a very active climate scientist working for NASA all these decades, and is someone who has made this case, exactly what you just said, that we're potentially underestimating how sensitive the climate system is to adding CO2. And I will say that if you look at the geological record of how much things have changed in the past, like ice ages and other changes, it can reinforce that point. And so just to help drive this home a little bit, here's his graph from 1981. This is published in the journal Science, which is kind of the premier science journal in the US. So this is from 1950 out to now, to 2020. And he was at this point in 1980, temperatures hadn't changed very much. And he said if greenhouse gases weren't added to the atmosphere, the future temperatures would be somewhere in this gray range. They'd sort of potentially bounce up and down. You get some warm years, some cold years, it's in that range. But if the climate system had different levels of sensitivity to the greenhouse gases we were adding, the different degrees here represent, if you double the amount of CO2 in the atmosphere, how much would the world warm? And we didn't totally know. Maybe it didn't warm that much. Maybe it only warmed, if you doubled CO2, it would only warm about 1.4 degrees Celsius. On the other hand, maybe it warms 5.6 degrees Celsius. So he ran a model that sort of simulated a future, and these are the different paths that he projected for how things should have changed based on these estimates. And here's the actual data. Whoops. Oh, come on, come back. Oh, I lost it. I'll show it to you like this. So what you can see here is that the actual observations have outstripped it. But it's a little bit misleading here. It's not because he was wrong and we were underestimating that sensitivity of the climate system. It's that we didn't expect how much emissions we would add over that time period. We've added rapidly more carbon to the atmosphere, much more carbon to the atmosphere than we had anticipated we would. And so in many ways, the rate of warming going up it's not because the physics is wrong, it's because of our emissions and the impact we're having is greater than expected.
There's also the issue of methane.
Yes, so methane, this is focusing on CO2, but they're absolutely including methane in these simulations and thinking about them. Methane, by the way, is much less common in the atmosphere. It's in parts per billion. If I'd have to get 1 billion molecules here in front of me in order to start detecting methane. But methane is a much more potent greenhouse gas because CO2, remember, has these 2 bonds that are absorbing energy, but methane has 4. So it can basically do twice as much absorption. And so it's a much more potent greenhouse gas. And that's why there's a lot of concern about methane being released from landfills, from natural gas drilling sites, from areas with a lot of feed, cattle. Those are all big sources. Rice paddies are big sources of methane. So a lot of human activity also increases methane as well. Yeah.
If you have the mitigation model measurements, what kind of mitigation are you talking about?
Yeah, that's a good question. So this assumes there are these different sort of storylines that essentially the Intergovernmental Panel on Climate Change, which is a group created by the UN based on a treaty that many nations around the world signed. They agreed that every few years they would assess the state of the climate. And so in order to do that, they came up with some storylines, basically imagined ways in which we might manage carbon in the future. And so that one with some mitigation is things like a substantial electrification of our transportation sector, other increases in renewable energy use. I can't remember if that scenario has a certain amount of nuclear, like increased nuclear energy in there as well. But it also incorporates significant increases in efficiency in our energy use. So it's not necessarily a perfect story for how things are playing out, but that one with some mitigation is somewhat close to the path that we're currently, the Paris Agreement that was put forward was generally targeting that pathway. And I'll just, since we're just at the end here, I'll just show you one thing about the energy transition that I think is worth everyone knowing. Okay, this is from the U.S. Energy Information Agency. And on the left, the boxes are all the different sources of energy. Oops, yeah. But on the left over here, are all the different sources of energy. So we use a lot of solar now, a lot of nuclear, a lot of hydro, a lot of wind, geothermal, and then of course natural gas. Coal has shrunk a bit, biomass, and then petroleum. And one thing that's interesting is that most of that energy, as it gets used, if you take all the things that use it and end up over here, most of it ends up as waste. So think about this is why electrification of cars is really significant, because even if you get that electricity from coal, the coal drives electricity that drives an electric motor in your car. Whereas when you put gasoline in, mostly what you're doing is making your engine hot. And so most of the energy that you get from the gasoline goes out as heat. And most of the services that we get are very small. So the huge potential here to reduce those kind of waste streams of energy to really improve our emission situation. And I'll just show you one more point here, which is the pink boxes are the different uses that we have: residential, commercial, industrial, and transportation. Almost all of the petroleum that we use goes into the transportation sector. So by electrifying the transportation sector, that would significantly reduce one of our main sources of carbon emissions. So these are the types of changes that people have thought seriously about targeting. This is why you see a lot of emphasis right now on electrifying transportation in particular. Yeah.
Is it possible for us to access all your slides on the website?
Yeah. I will definitely find a way to put these out. And I'm not sure the best way to share that, but this is part of the reason for us to have these handouts is that we are building a website and ultimately a resource space that will have information like these fact sheets. But if you use the QR code on the back, you can get to our website, and I will put a lot of these slides up there.
We're gonna post this on Geologists
Oh.
of Jackson Hole.
Yes, thank you. Yeah, the recording, and I guess I could give you the slides too. Could be on the Geologists of Jackson Hole website. All right, well, we're at 7 o'clock, so thank you so much for the engaged questions.